No. Yeah, yeah. Speaker. Okay, so our the speaker has to go off. Speaker. Yeah, so our galaxy, Milky Way galaxy is a barred spiral galaxy. There's a bar in the center, and these beautiful spiral arms. Look at it face now. And if you look at it edge on it, you have this, have that essentially roughly three components, but the disk also has a thin disk and a thick disk, and there are finer features. But roughly, you have a disk where there's a lot of gas, and this is where new stars are being constantly formed. And then you have the bulge in a very active place. Then you have the halo, and essentially the star formation is not really taking place. Now, with new observations from Gaia and all, we are seeing stellar streams and there's activity even there. So it's not really a dead place. So the size of our visible part of the disk is almost 100,000 light years to 180,000 light years. And the thickness of the disk is 2,000 light years thick. Right? Still, we compared to the size, it's pretty small. And it has about 100 to 400 billion stars in it. Mass about 1.5 10 power 12 solar masses, and this is the morphology of our galaxy. Okay, so we realize that there are many galaxies. They come in all kinds of shapes and colors. There are these beautiful ones with spiral arms. You have elliptical ones. Yeah, here you have a barred spiral and etc. etc. So once Hubble and Anderson realized that there were many galaxies, they started looking at most of the nebulae, and many of them were galaxies. And Hubble arranged them in a morphological diagram. This was based only on the morphology at that time on photographic plates and so on, what they saw. And he thought that there were essentially three kinds of galaxies: ellipticals, spirals, and lenticulars. Spirals, there were two types: normal spirals and bar spirals. And so, though this was just a scheme on the basis of the shape, morphology of it, but people started believing that this is how they are created. They are formed as ellipticals and they become spirals and barred spirals going through the lenticular phase. And there were some irregular galaxies, peculiar type, which Hubble didn't like, so he brushed it under the carpet. It didn't fall into his scheme. And there were people around the time who to observe, but had control over a lot of observation facilities, so he didn't let them see. Yeah. So this kind of a thing happens even today. There are strong. There's a dogma. And there's strong lobbies. If they believe in Big Bang, they don't let studies go and vice versa, which should happen in science. Okay, so the idea was they thought that matter falls in star formation spherical objects. Because of rotation, they start bulging on the equatorial plane, like all planets are bulging on the equator. And then the disk appears, so they become lenticulars. The disk is featureless. An elliptical one with the disk, which are lenticulars, and then due to whatever it is with our spiral lumps come up. And slowly the central region keeps shrinking, and they go from at A to B, where the central nucleus or halves open up in its grander design and form. Similarly, you have HB, HB, okay, this is the what was by Hubble, and there's some more morphological schemes and composition. Yes. Our Milky Way belongs to a collection of more galaxies, 80 or more small galaxies, which is called the local galaxies. They are Milky Way and Andromeda, both spiral galaxies. Andromeda being twice the size of ours. Okay. And then local groups either they belong to clusters and superclusters of galaxies. These superclusters make the whole universe. So here there are pictures of Mormon cluster and Lego cluster. And it's interesting is do you find morphology. So if you look at the central region where there are more density, more galaxies, uh, they seem to be more elliptical than lenticular galaxies. While the outer edges of these clusters have spirals. There's a strong understanding of feeling that there is a relationship between the density and morphology. Right? So when they are in close vicinity of other galaxies, then they merge into each other and they settle down and they become elliptical and lenticular. The undisturbed gives the spirals. Okay. So unlike the Coma cluster has over 1,000 identified galaxies, the larger cluster actually about 2,000 galaxies. So Virgo has a fairly heterogeneous mix of spirals and ellipticals, while is mostly ellipticals and lenticular and very few spirals. In fact, one of our students, Nagamani, she worked on the morphologies of galaxies in the Coma cluster, and I will be able to show those results now because we don't have. But it's interesting to say that. Then in this cluster environment, there's a lot of dynamical effect which keeps taking place. As these galaxies plunge through the center of the cluster, uh, there are outflows which come up. Yeah, because of ram pressure, cold gas is pushed out. And that can lead to quenching of star formation. Stars go down. So this is called strangulation. Okay. So there are some the images which you see here, these are the outflows which you see, these are pictures. You see these due to ram pressure, and here's an animation which shows how as the galaxy moves through this cluster, the inter-cluster medium is very hot. It emits so as it is going through, the cool gas gets pushed out and the star formation rates can get reduced. So you can see in the animation that there are these outputs there. And simulation, understanding morphology and various things. So the other was dynamical harassment establishing. So basically, harassment is when two galaxies go past each other, come close or collide, they disturb each other, and the morphology can change. It can change the star formation rates. It can uh, change various things. So yeah, so this is an interesting thing to study. You can do it both using simulations. Okay, so here's a simulation of spiral galaxies which are merging to finally end up to become a big elliptical galaxy. Right? So this is something the understanding which people had that ellipticals become spirals, but here we are seeing that spirals merge and they can end up as ellipticals. So this simulation also explains why you nuclear galaxies. For example, this NGC 4676, which is also called the mice. It looks like two. with tails hitting each other. And I tried to stop it at some point to show that we are seeing this in, we are just seeing this stage of the whole thing, right? Maybe, maybe, okay. And eventually they'll end up to become an elliptical galaxy, right? So in 1970s, Tumre and Tumre, two brothers, they did very meaningful simulations and showed how these spiral arms can be formed, how tidal tails are created, how bridges between galaxies are formed, and so on. And have these kind of strange, awkward galaxies. And the ones which Hubble was ignoring, neglecting, and not allowing people to observe were the most interesting objects. Long time people thought that galaxies are island universes. They are they have nothing to do with each other. Okay, they are right. So initially one galaxy theory, then we realized that there are many galaxies, but all galaxies are separated from each other, and and so on. And then now we realize that it's not so. Galaxies continuously interact with each other, like even in our local neighborhood, our Milky Way constantly an interaction 10 to the power of 9 years back, and which has led to forming of the small Magellanic and large Magellanic clouds. Must have been major galaxies which came close by, got ripped up by our Milky star and matter flow into that. And similarly, there are many other smaller galaxies which constantly fall and become a part of ours and so on. So there's a lot of cannibalism which goes on. And here's a picture of a giant elliptical galaxies. And in most of the star cluster, not star clusters, galactic clusters, the central region, like even in the coma, the central region, you find these giant elliptical galaxies, CD galaxies. The coma, they are galaxies which are sitting this center. They are ellipticals and huge ones. And they are the ones which are uh, merger remnants. Yeah. So if you see them in different wavelengths, you can see that it has more than one core. So it has cannibalized many other galaxies to become one big giant one. Okay, so basically what's happening is when you have these spirals come and merge, they churn up the whole thing. And can be an activity of star formation. Very often when star galaxies go past each other or disturbed, the gas gets compressed and gets funneled to the center, and there's a burst of star formation. And is the AGNs, the active galactic nuclei, and for a long time these were mysteries. But today we realize that it's basically these galaxies are more active than the others. The star formation rates are higher because which is triggering tremendous amount of star formation, right? So which is some kind of a shock or mechanism which is compressing gas to form stars. So looking at the bulge of a galaxy, you get to understand much about the whole history of it, and that's what we try to do. We have classical bulges, then you have pseudo bulges. Yeah. So these classical bulges, they are, which is hard to see at your inclinations. They are essentially featureless. They don't have firing arms or the rings. Contain mostly all old star of dust to start on the region. And currently they are kinematically hot. Means there's a lot of the dynamics in it. So, right. So yeah, if it settles down, if the velocities are low, then your kinetic energy is low. So when you say kinetically hot or cold, it basically implies that the stars have settled down peacefully, moving in their orbits, or they are moving randomly in orbit. The kinematically hot, then it is supported by the velocity dispersion of the stars. The pseudobulges, they are or almost flat surface. They may contain substructures like bars and spiral arms and rings. They usually show signs of dust obscuration, stellar, young stellar population, or ongoing star formation. They are kinetically cold, dynamically supported by the rotational velocities. And these two things also connect us with the scaling relations of galaxies, Tully-Fisher relationship and relationship, where you see that the mass of a galaxy depends on the uh, either the maximum velocity rotation. Yeah, so you can find out what is the mass of a galaxy by looking at. Yeah, this is used for spirals essentially, and the other one where a lot of uh, dispersion velocity, and with that you can compute the mass of a galaxy. Yeah, I have a slide on that later. And other than that, you have these box or peanut type of uh, galaxies. See, it looks like a peanut, right? There's a bulge here and a dip and bulge and so on. Okay. So, or it can look like a box. Yeah. Okay. So essentially, probably these are two major galaxies must have merged or in their process of merging, where the two cores are still separated, they've not coalesced to form one. So you have a boxy kind of. So this gives us an idea of what we are going to do in our exercises. By looking at these galaxies, generally we cannot make out the light distribution. How is light in falling and so on, right? But when you use some way of calculating light profiles, we can understand how they, what kind of bulges they have, and hence we can try to infer how were they created, the merger. So, yeah, another important thing which is an established thing is the size of the bulge and the black hole mass at the center. There is a direct correlation between them. These which have a smaller black hole at the center, their mass, the bulge is smaller, and as the black hole mass becomes larger and larger, this bulge becomes large. So there is a direct relationship. Yeah, without a doubt, it is established that black hole and the bulge. And remember, the whole very simple that spirals become elliptical and so on. It's an ongoing process. The galaxies are constantly changing. Spirals can merge to become ellipticals, and if not all the gas gets consumed, then the settles down into the plane and start taking place. And since they are new stars being formed, they are bright stars, then you start seeing them as a spiral galaxy. And then because of resonances and all, the stellar orbits change, and that can lead to the formation of a bar, can become a bar spiral, and the bar again can break up to form spiral. And so it's a continuous process where spirals can become ellipticals, and ellipticals can again settle down to become spirals and so on and so forth. So saying what is the morphology of a galaxy is just at that time what we see it is the morphology. Other than that, also remember that when we see a different wave bands, you see different features in it, and you see it as a different thing. Yeah. The analogy of the elephant in Six Blind Men given yesterday, the same thing happens. In one waveband, you see it as a disc, in another, you see it in X ray, another one you see, right? So you have to compose, you have to have observation in all wavebands to understand. So, by morphology, by looking at the surface brightness. And the surface brightness is the amount of light contained in an area at a particular point in a. So you take a point in this space and you make a say square of side of length d, and if we add distance small d from that thing, then it's an angle alpha, which is d by d, right? So I'm taking a small patch on this, and as how the distance I go, you have the distance, and okay, so you have this alpha, uh, the luminosity of the galaxy in that area, and suppose that's zero. That's which you are getting is L divided by 4 pi d square. And if you notice that this thing remains constant irrespective of how far we are, because, right? So, uh, because you're, as you go further away, you are look at the same angle subtends a bigger area, and the intense surface brightness you collect is independent of the distance which you get. So your intensity is m pi alpha squared, and the surface brightness, but yeah, this is what I'm writing. Yes, you have to keep in mind that going too far, if the redshifts are very high, then you have to include into it the cosmological dimming. Right? So this becomes an important thing. Otherwise, you will get some wrong estimates. Yeah, and you can calculate the magnitudes and so on. Okay. So for surface photometry, what we do is for a galaxy, you make concentric rings, annuli of similar area, and you try to measure the light whole thing. So you put annular things which you should be doing it, and you try to find the intensity of light, how it falls. And the way it falls, how it decreases from center outwards, about the bulge, nature of the bulge, and hence the nature of bulge tells you whether it is a pseudo bulge, classical bulge, and so on, and then you can understand how it was created. Okay, so for extended objects such as galaxies, uh, as opposed to the point surface such as stars, we have to calculate this surface photo, because you can't individually collect light from in each star and calculate. Yeah. So that's why you take a small area and see how much light is coming from a certain area, and you calculate this. So surface photometry is used when the magnitude of the individual stars cannot be measured, but only the smooth integrated light is observed. Okay, so the gal have, yeah, this is the basic idea. And so you have this hydral, in this Abel cluster at a distance of megaparsecs, and even the best of telescopes, HST and all, cannot resolve in general stars, right? Yeah, so when you're doing photogrammetry, there are things which you have to take into account: the point spread function and the background subtraction. So when you are imaging an object, you not only record the light coming from the object, but also the light coming from the back. Okay, so you have to do the background subtraction to get it. And secondly, another thing which we realize is that because of the atmosphere, even if you have a point object, it gets and you get you can never image a point object as a point, but it gets smudged, right? So you have to correct. So this is happening with every point in it. So you have to make a correction, the point split function, and make a correction of that. Okay, so you make these two. And there is this relation, important relation, which is called the Sersig. This is the Sersig index, uh, where this shows how density falls as you go from center outwards. It's a function of R. And ID is the intensity within the effective radius. So effective radius is that radius where half of the light of the whole galaxy or the pixelated object residing in. So that is the RE, and the intensity at that effective radius is the ID, and e to the power of minus B n R 1 to the power of n. Okay, this n is called the Cerseic index, and generally the disk, exponential disk, n value is 1, right? And when n equal to 4, this is the, you get the Divacular law. And these are for the typical elliptical galaxies, right? So by doing some galaxy, uh, uh, we have an image of a galaxy, you fit the profile. There is a program called the GalFit, and you see how the intensity is falling. And by looking at the fall of the light, you get a value for Cerseic index, and that tells you what kind of a bulge it has, right? So, what is done is if it's an elliptical galaxy, then you just fit, say, a single model. But if it's a uh, galaxy with a bulge and a bar, then you can fit it with multiple components. So the surface brightness profile, we'll see how, yeah, other than that, you have isophores. It is a closed curve connecting surface brightness. So by looking at these isophores or contour plots, you get to see what's happening. If it's an undisturbed galaxy, then it's an elliptical one, and they are perfect ellipses which, if there is there are two cores in it or there's disturbance going on, then you see that these are distorted. Like you see here, this seems to be a disturbed galaxy. Some kind of a merger has happened and it has not yet settled down. So you look at how this you can understand. So yeah, so essentially this is the effective radius, and uh, yeah, so in galaxy photometry, if you have a galaxy, you can have multiple components. You have the central, you have a bulge, you can have a bar, you can have an extended bulge and a halo, and you fit them all together. Okay, so for example, you look at, we have elliptical galaxies, they look very simple normally. They are roughly round or elliptical. They have smooth light distribution, and there are no obvious patches of star formation, and there's no obvious dust lanes, except some you do see them. But a detailed studies show that they are not really as simple as they, but they have large range of shapes, oblate or triangle. So if you look at the light profiles, you may have triad. You don't see any symmetry from any axis, right? So sometimes you have, it's take a ellipse and rotate it, so you get, if you slice it up, you get circles here, right? Or but there are some where you see that they don't have any axis of symmetry, right? So that directly indicates that this is some kind of a material element. By naked eye, you may not be able to notice it, but by doing some kind of scan. So they have large types of shapes, and the type of bulges, the way the light also falls changes. They can be oblate. There is a large range of luminosities and concentrations. The rotation versus pressure support varies, and they have cuspy or chord centered ones. Looking at this by that how, from our vantage point, from the point where we are looking, we are fixed. We can't move too far. So if you happen to see edge on, you think this elementary like that, it may be tilted towards, or it may be looking at you straight on. So, what is the inclination angle itself can make us feel that the galaxy, we will, we infer this morphology distance. Angle determines very much the shape of the galaxies. Okay, so, yes. So we do this ellipse fitting. It's a separate task which we do it using DS9, and we see how this light is falling, and you can try to fit different lines. Like for example, this one, you can fit one here. So this one component will give you the bulge, and the other one will give the disk, right? So multi-component you fit, then you may have different kinds of light profiles and describe the features better. So what we'll do is we'll use DS9 to put concentric circles and try to do this. So maybe I'll stop here now and do that, and then we will continue if we have time for other things. So, so we'll start with this DS9. Now I want to share that with if there are people online, do that. Anyway, yeah, so DS9, uh, yeah,
It's getting covered. Just think, get it down.
yeah, I know.
Just drag it down. खींच. बस.
Okay, so we start off with this DS, and uh, you can go to analysis and go to image servers, right? You need to have net connection. You're going to either you have the image sitting on your system, or we'll try to download. So there are different image servers: DSS SAO, DSS ESO, STSI, right? And sometimes some of the servers maybe if it doesn't, I've taken and here we specify the galaxy. Okay, so for example, if I say you can give the object name, DC 54565. Okay, I don't know what the RA and deca for this. I just named and I said retrieve. So it's looking up NGC 4565. It's trying to get it. And depending on how good is our net, yeah. So it has loaded it and got its RA and deck and it has given you this image. Okay. And in case the object which you look at is not, you are not getting the whole thing, or you are getting too much of outer region, you can change the region which you are width and height. You can, the default in which I got this time is good enough. So it is in arc minutes and arc seconds, you can do that. Okay. Next thing you can do is come to this edit and click this region. Click this region. Normally, when you start DS9, it none is the option, but you go to the region. Okay. And once you do that, this region gets uh, activated and you can do things here. Go to region from top, go to shape, and you have circle, ellipse, box, vector. You take elliptical annulus. Okay. And yeah, so once we have done it, click in the center of the image and it has created, I've taken one, so it is created, but we want it to get shifted. So now you click the green ellipse, oh, sorry. So when you click this, double click it, it opens another window. And here you see annuli is only one, say 10 of them or 15 or 20. 10. And again, look at the angle which it has given us 359.79. So almost 360. So this is 360. Yeah, it is just slightly below, and 360 would be 0. Okay. So we this should look like 45 degrees to me, roughly. So I'll and press generate. So once you press generate, you get all these annular regions, and then you apply. And there you see pretty well aligned.
The DS9 is coming. So share your whole screen. Stop share. And now when you're sharing, share your screen here.
Okay. Okay, so right. Now another thing you'll notice is that the inner one is starting from 0.0188 and outer one 28. So if I want to go deeper, I'll just add one more 0.0018 and again I need to generate and then apply and you see it's filling it up. And you can increase the annuli to say 30 or so, whatever you 130 will be too much. 30. And the outer one also you can go much further off. Okay, so let me generate and apply. In fact, I can even use this to pull it like that. So it has created annuli across this and it is filling up the whole thing. In fact, go a little beyond the galaxy. If the tilt you feel is not correct, if 45 is too much, if it is 43, is more or less we've got it right. Generate and apply. It's fitting well. And now you click this analysis, and there are two things. One is statistics. So this gives you the statistics about each region, what is the sum, what is the error, and so on. Surface brightness, so on. But more important is I'm interested in looking at the radial profile. And you are getting this kind of profile to the galaxy. Yeah. In fact, you can, since the numbers are large, I can go into graph and I can take log of x and again take y-axis also log of it. So when you convert it to, then you see that the light, yeah, if you, when we saw that image, we couldn't realize that the central region was so much brighter and yeah. But here you see that it is, yes, so we can take two lines, one and another one, right? So that will show you two components of it. One will be for the bulge and one will be for the disk part of it. Okay, right? In fact, to get that Searsic index, I'll leave it as an exercise. What you can do is click this file and say download data, and you can save it as some data. So, what was the name of this galaxy? GC NGC 4565 dot dat, and just see where it is. It is saving in. Oh, what did it do? Sorry, I should have sent save data. But so that will be have that file. It is sitting in downloads, and here, here, and if you it will open using some application, but what you should try to do is try to open through TopCat, which you learned yesterday, and again you can plot with TopCat, you'll get something similar, and you can see the Searsic profile, and you will realize what kind of a bulge it has and so on. Now, if you want to empty this whole thing, you can go into frame and you can say frame, so that goes. Yeah. So now I'll repeat the same thing again with some other galaxy, maybe an elliptical one this time. So what do we do? Go to analysis, go to image server, TSS, this ESO site is behaving well today. So come here and then say M13. It doesn't matter whether you write capital M13 or small M13 or with a gap there. You can try it out. It shouldn't matter. And then again, I'm retrieving M13. So it is looking, contacting server, and it has given you this. Right? What did we do next? Uh, we had already, region was already clicked, so it is fine. And now when you come to this region, you can come here and go to shapes, go to ellipse, look circular, you can take circular one, and somewhere in the center, I will click and double click that. It opens the parameter window, and here you can increase the number of annuli to say 10, apply, and generate. Generate and then apply. 10, generate, and then apply. And again, the inner region is pretty much empty, so I make that this one and I increase the outer one. Either you can do it, generate, and apply. Okay. No, this is totally gone bonkers. We should have taken, instead of ellipses, we should have taken maybe circular ones, isn't it? It from here.
Yeah.
No, but it is becoming a bigger and bigger ellipse. Yeah, yeah. And remove region. So we can put, say, 30 of those and apply, generate, and then 30, generate and apply, and you pull it out. And central region, fill it up from center. Okay. And now you can click this, go into analysis and look at the radial profile, and it gives you the profile of this. So you can try it out for different ones, and can get profiles, and then you'll have to get the Sersic index. Use any method you like to show what function fits. Either you need two components or single ones. Uh, Another thing we can do right here is go into analysis and get into contours. Yeah, so this isophones. And you can get into contour parameters, and you can change the level of smoothness and the level vary, and you can get to see how light is varying. And yeah, the low limit is 2749 and high is 14. So you can increase this even more because the central region is pretty much bright. So what if we make this, so only the brighter regions we are getting, low and high, and so you can do these contour plots and so on and see how these contours, these are marking regions of same city with a closed curve. So if it's a properly virialized system, then you get concentric elliptical ones. Otherwise, you see, for example, the other one, NGC frame. You can even have two frames here. You can add another new frame and stack them up side by side and do it. Analyze. See, some interesting ones I have kept: 3854, 3854, retrieve. So this is the galaxy, and you can do the same thing. We can, yes. Now the contours thing was on, that's why it all directly plotted it on that. Yeah, so you can change the parameters and play around with parameters. And okay, so you can see these things and just zoom in, zoom in. See that? You see how the light intensity is changing in. So you can see spiral arms and all. Otherwise, you may not be able to see it with naked eye through the figure, but through this you. So DS9 again, it connects with all the virtual observatory, the other tools, and yeah. So this, see, already it's connecting to searching from the servers and. Okay, so this is one thing. So you do the ellipse fitting and see these profiles, and you can have multiple. You can break the galaxy into various components and do it, and kind of searching one it is, which tell you about the bulge of the galaxy, the disk of the galaxy. That's the disky one and so. And for gas component, typical ones, and these are the Telly-Fisher relationships which we can use. The luminosity falls by uh, this velocity dispersion to the power of 4. And you can understand the galaxies better. A much more sophisticated way of doing it is to do it using Galfit. It's a program which will run only on Linux or Unix systems or in Mac. It won't run in Windows. So Galfit is used to fit to these galaxies. One of our students, Navani, she took, I think, 284 galaxies, and she first did a primary single Cerseic fits, and then in some, when the errors are fit using multiple components, and see when you get the right thing. So objects which normally, yeah, these are some of things. You see, what this Galpit does is, this is the image which you have here. This Then you fit uh, uh, you fit a mathematical model. Yeah, so there's this function which shows you how light falls from center. So you roughly give this inclination and whether minor and major axes are different or not. In this case, it's pretty circular. Then this is the model, and then you subtract that. And if nothing remains, then this model is a pretty good fit. In this case, you see, you are fitting the model, and when you subtract that, you are seeing features. So though we may think it's an elliptical galaxy, it's really there are spiral arms there. And similarly here, you think this is a spiral galaxy, a bar spiral. You can see a bar pitch here. So here you shape it two components to it, the bulge component and this component to the outer region. So you see a region, right? And a disk. And then when you subtract these two, you are seeing feature like a bar there. So it's a barred feature. It's a barred galaxy. Yeah. So there are things which in it. Okay, and then you look at the total bulk to total light ratio, and you further look into details of it, and you can get finer and better estimates of morphology of a galaxy. And from that estimate, and I try to understand what processes going on or what has led to creation of this galaxy. Or so in the coma cluster, what she found out mostly the central region you have elliptical acid, right? They or lenticulars. So the merger must have happened much earlier, and now they have settled down well. There are very few spiral galaxies in the outer regions. So overall, she studied the central core region, and the outer core region has some spirals. Mostly they are elliptical, and yeah, so you fit different profiles, and yeah, you have a disk component and the bulge component, and together you get another. So classically bulges, these are, yeah, we have. So how are they? There's a whole history formation of massive elliptical galaxies, the early disruption, they disappeared followed by mergers, mostly minor mergers. And classical bulges could also be formed from mergers, but difference in properties of classical bulges and elliptical indicate different merger history and need to. So these differences could be because of the ratio of major to minor mergers which happened, the ratio of gas flow to gas rich mergers, the total number of mergers, and the merger orbiting parameters. All these make a difference. And there is a refined classification of galaxies given by um, Cormandian builder, where you have ellipticals, boxy, disky, and lenticular galaxies. Lenticulars A, B, C, and spheroidals, and your S is spirals, and then all these indicate how what is going to be studied. And the same thing can be done uh, using simulations. Another student of ours, Sweta, has done simulations using gadget. And using gadget, she has done some simulations, and she is looking at minor mergers rather than major mergers. So what are minor mergers? 1:10 or 1:100 ratio. The one galaxy is 10 times more massive than the smaller ones. So Priya, Sweta, and I am working on these things. We have published some preliminary results, and she is changing the gas frequency, the gas percentage in the galaxies, and seeing how the disk of the galaxy change, star formation rates change. So what she is essentially seeing is when you have more gas in it, there's a greater star formation rate, which is pretty understandable. But when there's more gas in it, then the thickening of the disk is not much. So as you keep increasing, you would expect the disk to become thicker and thicker, but it doesn't really happen. It does get thicker because gas is being flowed in, but it is not increasing by the same amount as it's coming in. It's right, and basically that's because the gas acts as a absorber. It takes in the kinetic energy, and so the thickening of the disk is not much. You are increasing the percentage of gas still. Yeah, so these are the parameters which use 1:10, and the primary disk mass was 4 into 10 10 solar mass. Secondary the distance was 100 kiloparsecs, and it redshifts 1 to 0. This is the code. She started off with gadget 2, and now she's doing with 4. DICE is a program which is used to generate the initial condition of it. And gas fractions vary from 0 to 40%. And the dark matter halo component is this Navarro the profile suggested by them, which is a standard the dark matter halos. Then you have the stellar disk, exponential disk, gaseous disk exponential, and the bulge is the Harquist. So she created galaxies with the grid simulations, and yeah, these are the results. Conversion rates of new stars which are found, and so on. And the work is going on. So yeah, so with this I'll stop now. Thank you.
We reconverge at 2:30. 2:30.
2:30.
We were supposed to walk to the guest house and walk back.
Oh, the phone.
I think the food is in. Food is.
Yeah. Take- but-
The mother of the galaxy is the mother of the galaxy. Yeah, yeah. That kind of. Yeah. Sequence. He saw that the two galaxies, even when they pass each other, particularly there's tremendous amount of energy which is absorbed. And these energies are equal to the binding energy. So this means it can lead to something of the galaxy. Right? These processes are very small, very slow. In a lifetime, we don't notice even snapshot. So you right, it takes billions of two galaxies come together. It's if they are each other with high velocities, then they just go through each other. Nothing happens.